You guys are gonna come back in December?
We're only staying for 10 days because of Thanksgiving break.
And they've got you have to package things and figure out what things to ship.
Yeah.
They've got to sell their house there. They have a house here.
Oh, yeah.
They're only going 10 days in Germany?
Yes.
Okay.
I think
So
we'll
they have to be back in school.
give a couple more
Do you have
minutes.
makeup work you have to take with you?
A bit, but we're
So-
only missing 4 days of school.
Total?
Is anybody online?
I mean, I just literally started it.
Oh, okay. I'm just
Okay.
kind of curious if
So-
anybody actually made it. One of the things Jan
Took me-
wanted to talk about was the
I'm not
party.
used to being up late.
and I think she wants
So-
to talk about who's bringing what
Takes
at the
me a
next
while.
board
My
meeting.
dog's looking at me like, what are you doing?
Sure.
Yeah, well, it takes a little bit.
Have it on the agenda.
I don't think we
Takes
need
a lot
to
more
talk about
adjusting
it
at our
too
age.
much here, though.
So I was telling these guys, you guys starting up?
Maybe in a minute or two.
Okay. I was telling them, and I looked at Astrometrica's homepage, and it said it'll open fits of any size as long as your computer has the memory.
Right.
So I can't figure out how come Astrometrica won't open up an image with the new camera. The new camera's kicking out 5 megabyte
Yeah,
files.
that's treatment, you know. Yeah.
Because I was telling them I kind of like Astrometrica because after I took an image, I could resolve it, find out where actually am I pointing, and then make any adjustments.
Make sure you're in the right
It appears
spot.
that since I did 9 objects and only could find 2, I started thinking maybe I'm not pointing in the right way, which is what I was trying to text you. And the coordinates I asked it to move to were showing up in the bottom left coordinate. So if the position angle was not going up diagonally, then that thing was going to be out of the field of view.
Right,
And maybe that's the reason Tycho could not find it.
could be.
But I did a 19.8,
Uh-huh.
and it was other observatories were producing data,
Yeah.
and I took 150 images
So 10 seconds
of
each.
like, did you look it up?
Well, I
It was
didn't.
like 10 seconds. It was a pretty fast mover, I think.
Yeah, but, yeah, I don't know. When it gets into big numbers of images, it has a little more trouble, I think. But, I mean, he used it, this Daniel Parrott used it for 200 images. So
Yeah.
it's a combination of probably of the image size and the number of images and the timing factor.
Are you talking Tycho?
Yeah.
Okay. So I didn't start with 150.
Did you get Astrometrica to work though? with
No,
those
well,
images?
I've tried a few times,
I couldn't get it to work.
And I
on
can't-
mine. Even my images, even my short, my small scale, because I think what happens is, when you go so low in pixel size, that it has trouble distinguishing between that and cosmic rays or something else, so it may kick out actual legitimate stars that he thinks are noise.
it wouldn't even open the file.
Really?
It would just open up, I can't remember what it said, but something, it wouldn't even take it.
Well, I can get Astrometrica to take it, but what happens is it never solves. It can't find the solution. And I'm not sure why, but ever since I switched over, and I go back and forth because I still have the CCD camera, so I switch back and forth between the two, and neither one now will take it.
Okay.
So I'm not sure what's going on in Astrometrica, why things are changed, what's changed that Astrometrica won't accept anything.
Okay.
It
Well,
won't solve
it's supposed to
anything.
clear up for a few hours later. I'll
Is it?
try to not double J2000, because I think
Yeah, I
that
think,
was a problem a while ago. We turned one of
Right.
them off, and maybe one of them got turned back on.
I think just see, you can go into either one and make sure that they're not both in J2000, or both in J2000, that's an issue.
Sorry.
In a
Well-
nutshell, what were you talking about? I'm listening. And I'm trying to make sense.
I don't know either. No, we were talking about programs that we use to do the analysis for astrometry. In other words, positional data
Yeah.
on different objects, okay? So we can't get some of our old software that we used forever to actually work with the newer images because it's kind of a different format than it's used to. And it should take that, but I'm not sure why it's not taking the ones he's got. It takes some of the images that I've got, but I can't get it to solve anything because it can't find star positions for some reason. Even though, I mean, you got catalogs that say where all these stars are, and you get the software that wants to try to solve and find out where exactly you are according to your coordinates, and it never can find it.
What day? Images.
So
Last night.
I'm not sure why. I haven't
17,
done more
I opened
investigation
it.
to find out.
In Naturmetrica?
Mm-hmm. I mean, I'm on the PowerPoint computer right now.
You opened in Astrometrica an image?
Yeah?
Huh, that was one of the first.
Well, maybe we should go ahead and get started. Should we go ahead and close the door too? I think I propped it open with one of those hangers. So,
The very official method there.
well, you have to adapt to the circumstances. So, welcome everybody. Glad to see a good turnout. Let's see. I know do we have anybody online too?
Let's just remote it in Astrometrica.
Let's see.
Well, it may be some settings that we've got in our Astrometrica that's not.
Good question.
Yeah.
Maybe one.
Okay,
Oh,
well,
no, that's
if-
me.
Oh,
Okay.
and he used
Well, if anybody's watching online, welcome there too. Let's see. Should we go around the table? I think we all know who we are, but maybe we'll, for the benefit of some new faces. My name's Doug Gooden. I'm the president of NEKAAL.
Tony Castaneda.
Sanford Pomeranz and my grandchildren, you want to introduce yourself?
Sven.
Sven?
Nice to meet you guys.
Yeah.
Angel Romero.
Gary Hug, the dinosaur.
Dave Cromer.
Russell Valentine.
Okay. Let's see. I don't know if we really have much in the way of news or announcements this month, do we? We're kind of headed into the period of time when holidays sort of disrupt our meeting schedule, so I don't think we got any public nights scheduled anytime real soon, right? I don't think we have any
Until
members nights until sometime in
February or
February.
April, or March or April usually. We haven't set the calendar.
And I think the next general meeting is actually in January, right?
I think so, yeah. It would be on Christmas if it were.
Yeah. Otherwise, yeah, we would be meeting on Christmas, which I don't think anybody wants to do. But we do have one thing that I was asked to remind everyone. We do have the Christmas party coming up. This is December 3rd. It's at the same place apparently that it always has been, Snyder's Cabin in Gage Park. I was asked by Jan to make a reminder of this, so I stuck this in there. Jan says that she is planning some surprises, including some surprise awards, and I don't know anything about this. This is apparently a secret, so I'm curious to see what will happen. But yeah, if you can make it out to that, please do. It's
Don't know what time, but
have we figured out a time yet?
I don't know what time.
I don't know. Maybe we better figure that out. It's getting close to the 3rd. When does it usually start?
Is Janelle on?
No,
I think it starts usually at 5.
That's what I thought too. It was usually kind of a 5 o'clock-ish.
Oh,
sort
that's
of
right.
thing.
I've got to do that thing mailing.
So, anyway, and also, by the way, if you need to get an election ballot in, go ahead and send those in. Gotten a few of them, but if you're planning on voting the election, send that in. I think the results get announced at the party. Anyway, I don't know. Has anybody got anything they would like to say?
Well, we actually got the mirror in and it's working now, so we're getting some pretty decent images off of it. One thing with this new mirror, what's going to be a little bit we're not used to, I think, is because it's kind of a loose fit, so it gives it a little room to play. So you may end up with temperature changes. You may have to adjust the mirror supports a little bit and make sure that they're all snugged up to the back side of the mirror surface. And it's easy to do, but I'll have to show people how to do that. And also the spacing and there may be a little bit of adjustment with how things line up with the imaging train to the mirror. So as things settle in, you know, there's a lot of tension on parts of it, and as things settle in, it'll shift just slightly. So we'll probably have to tweak it a few times, but keep in mind that because the mirror is pretty sensitive to pressures, so we have to be aware that if it starts looking kind of wonky, that we may need to go in there and adjust that again. So.
Is it?
And it's easy to adjust. So
Yeah. Is this one more sensitive because it's thinner?
yes, basically.
Yeah, which makes it lighter, obviously, which is good. But
Well, it makes it lighter, but it also lets it distort easier.
yeah.
So, you know,
Okay.
the last mirror we had was 3.5 inches thick.
Right.
This one is 1 3/8 thick in the center. So it's a lot less glass.
Mm-hmm.
So,
Well, I know I would certainly be interested in kind of learning the ropes a little bit better. I kind of felt like I got sidetracked a little bit. I'm kind of hoping to get back into that. Anything else?
Sky Telescope on their website says that I think towards the end of this month and starting in December, there's going to be a couple of comets that'll be high in the sky, not visually bright enough, but close, that you
Telescope.
could pick up with a small scope or binoculars maybe.
Okay.
So it's on the Sky Telescope. It's their main article. So we should be
Okay.
able to catch those at least through Tom Bond. Share that, but a
And
lot of
that-
us have scopes. You probably could find them.
And that's going to be when?
I think it's into December. It's
Okay.
not. I think now you can find them. They had some images, but in December it gets better, I believe.
Okay.
and Didymos is still a comet now because of the impact.
Because it's still leaving the trail of debris
As far as I
behind.
know, yeah.
Yeah.
I haven't imaged it for a while, but the last time I imaged it was probably several weeks ago.
It's still kind of showing the effect of the collision, right? I mean, it's
Oh,
kind
yeah.
of the collision kind of did what they.
Oh, yeah.
Thought that it would
Matter
do.
of fact, they thought that it was gonna make about 2 minute per day change, and it ended up making a 15-minute per day change, so much more than they thought originally.
Okay.
Hope for humanity yet.
Well,
Either that or, you know,
I think
we'll just play like the dinosaurs.
I think NASA kind of does that sometimes. They sort of intentionally underestimate
Oh,
stuff so
yeah,
that when it's
yeah.
better, then it's like, whoa, we did so well.
Yeah, look at us.
Yeah.
Yeah.
Which kind of brings me to any other announcements? Anything?
Well, I shared out to the membership that Gary is still ranked as one of the top. He's in the top 20 at least. He was number 11, and then it got down to number 12. Or he's there for amateur astronomers, other than the big skies on contributions on NEOs.
Yeah, and
So
the thing that struck me about that list was that I counted who was ahead, and I think only one other non-professional, right, was in
Right.
that list. Everyone else were these huge, well-funded,
Yeah.
well-equipped surveys.
and the list is from lunar cycle to lunar cycle. So I'm guessing either full moon to full moon or new moon to new moon.
Which is gonna make it very weather dependent.
Yeah.
Yeah,
But shows his hard work.
yeah, that's, yeah. Let's see.
Shows I have no social life, is what it shows.
Yeah, but this is more fun. All right, so moving on. Okay, news. I didn't have a whole lot of time this month to look up stuff like this, so this is a little short. These are just a few things that kind of caught my attention. First of all, finally, Artemis launched. It sat on the launch pad for over a month because it takes a very long time to get those things back into the building where they build them, basically. So they let it sitting out there. I think it went through, 2 tropical storms, or a tropical storm and a hurricane or something like that. They finally launched it, though, so it's on its way to the moon. It is the most powerful rocket ever launched. It has about 8 million pounds of thrust, which the old, the Saturn V, the one that went to the moon, was 7.5 million, which is, so this was actually a more powerful booster than that one. And
Surprisingly, only by 500,000, so
Yeah.
it really wasn't that big.
wasn't really that much. Yeah. but it's going to be, I'm going to be really interested in watching all this unfold, because from what I can understand, they're going to attempt the flight to the moon after a really small number of launches. Like it may be, there's one more and then a landing attempt, which if I understand it, they haven't even figured out how to get the landing vehicle done, or I'm not sure that's ready. So anyway, it's going to be really interesting to watch. But you know, I was as a 9-year-old absolutely spellbound by the whole moon landing thing. You know, so this is something I'm really looking forward to watching it unfold. So anyway, for me, this was probably the biggest piece of news. And I actually watched a lot of the video of the launch, so that was fun to see. Here's another one that actually bears a little bit on what I plan to talk about this evening. So one of the Saturn moons, I like the way they said this, may be more habitable. Like, you know, there's a continuum of habitability, basically. More habitable than thought. And what they've actually found was that there's phosphorus here, which, you know, if you think about the key elements of life, phosphorus is definitely one of the ones. So again, this is not any indication that there's actually anything living there, but it does mean that Enceladus may be an abode of life, or maybe even more. There's even more of a chance it may be an abode of life.
So obviously it's a spaceship because of all the.
Yeah, you can see the thrusters down here. I mean, sooner or later they'll fly back to wherever they came from, and that'll be a big surprise. Here's one I like this one because, you know, this is probably ultimately what'll happen to not us necessarily, but our system. You know, our star will turn into a white dwarf at some point. And what was interesting about this one, at least to me, was how mixed up everything got. So something about this process of stellar evolution leading to this kind of end state of a white dwarf really messed things around in this particular solar system. Apparently ripped the planets apart. They got inside the Roche limit probably of the white dwarf and got literally torn apart by its gravity. But then all the things that would have been its Kuiper belt, all these icy chunks of stuff, were mixed down in with the exoplanet stuff. You know, and so somehow this whole thing got very, very stirred up by this whole process of the star kind of going through the end of its life and evolving into
Would that have been after? I mean, doesn't it go into a red?
That's what
and then that would probably take up a lot of the solar system and crunch it there.
Yeah.
To start with. So I don't think it's just because it went to a white dwarf stage. It's because it
went through that whole process. Yeah.
It may have been a little bit rough.
Yeah, and I think that would be the same kind of ultimate trajectory of the sun. It'll become a red giant at some point. It's the kind of star that would do that. So, but anyway, I thought this was interesting because it kind of showed kind of what the end point of our own system may be. Some, you know, many years in the future. This was in Universe Today. This was one that it's always kind of interesting. This is the University of Sydney in Australia, some work that was done there. And what they found was that there's these things embedded in the Andromeda Galaxy, which is like, what, M31 or 33, 31? There are these things embedded in it that are kind of different than the entire, you know, rest of the galaxy. And the theory, I guess, is that at one point this galaxy just swallowed other galaxies, right? And that's apparently not a particularly unusual thing. In fact, I think at some point the thinking is eventually we'll get swallowed. It won't be anytime real soon, obviously, but and so they've found these bits of material in there that are maybe remnants of these other things that got swallowed. But what was interesting about them was that they were kind of in two different age cohorts, which sort of suggested that this happened kind of episodically, like, you know, something got eaten, and then some time went by, and then something got eaten, and then time has gone by. And so they found this.
And our own galaxy is swallowed up. We know our own galaxy is swallowed up other galaxies.
There is actually a structure. I
Yeah.
think maybe it was a news thing last month or the month before where there was some kind of foreign objects in our galaxy that are kind of a different population. So I thought this one was kind of interesting. This is University of Sydney. And by the way, is anybody getting tired of seeing this? I mean, just as a kind of way to wrap this up, it seems like every week
I know.
I've seen an article that's
Shows
like,
up on Facebook.
the world is coming to an end, and you know,
clickbait.
yeah, it's exactly what it is, and of course I fell for it, so I, I'm part of the problem, I guess. 110-foot asteroid Terror, coming near Earth tomorrow, which actually I guess would have been, about a week ago that this came near Earth.
And NASA reveals
It's a blistering speed.
Well,
yeah.
they travel between 20,000 and 60,000 miles an hour. Take your pick, it doesn't
Yeah.
matter.
Yeah. But anyway, this one would have been, I guess, big enough to have actually survived the trip through the atmosphere. I mean, it's probably above the limit. of-
110, yeah.
Would
probably
penetrate.
Would be 110 feet, that'd be at about 30 meters, yeah, probably survive.
It's probably about the same size as the one that made Meteor Crater in Arizona. It was about, I guess, about 30 meters purportedly. So-
Depending on what it's made of, yeah.
Yeah. So, if this thing ever came through, it could make a pretty big hole in the ground if it hit land, and pretty big splash if it hit
But
the
it
It
was
ocean.
doesn't even come close if you read, if this is the same one I read, it's like 3 lunar
Oh, yeah, no, they're not
distances away.
anywhere close, yeah. Every once in a while, one has actually come closer than the orbit of the moon, and that's really unusual. But, yeah, these things are, millions of miles away, or probably at least hundreds of thousands of miles away. But I don't know, this particular one was a technology website. I can't remember where, but
HT Tech.
yeah, HT Tech. I think it's in Hyderabad in India or something like that. But anyway, so I just thought I'd throw that in there as kind of something I'm getting a little tired of.
Hyper trash
seeing.
tech.
Yeah. Anyway, so
Janelle said in a meeting that the December holiday party is at 6 p.m.
6 p.m. Okay, holiday party, 6 p.m.
Snyder's Cabin Gage Park.
Saturday the 3rd. Be there or be square. Anyway, so yeah, those are the only news items. I mean, these are the big ones that kind of caught my attention because, like I said, I was a little short on time this month, so I didn't
I
have
heard one of them refer to dinosaurs, but it was some weird, like nothing has happened since, nothing this big has been here since the dinosaurs or something like that.
Yeah, but I don't
But
think
it was such trash.
Yeah.
The way they put it in there, it was like, technically, that's kind of wording is correct, but it's always a different meaning. It's always trying to draw your attention because dinosaurs and, extinction will go together. So they use dinosaurs in there, but dinosaurs have nothing to do with it.
Yeah. Well, I guess the only fortunate thing about it to me is that these are probably not widely read sites. So this is not going to end up being
Yeah.
like, the kid continually crying wolf, and
Yeah.
one of these days a wolf may actually show up. But anyway, it was. I've seen one of these. I'm serious.
Yeah, you'll see
Probably
it first.
once a week. There's an article saying,
And the ones
giant
that,
killer asteroid is
the
headed
small
over.
ones that all of a sudden they find and they're right on top of us and they're really close.
Uh-huh.
They just like
Yeah.
10,000, 20,000 miles off the surface. Those are close. They don't ever report on those.
Yeah.
Was there something, it was a while back, maybe within the last month, about something that was hidden from the glare of the sun?
Yeah,
Do you recall?
there were some. They were. What are the ones that orbit?
That one got spotted though by a spacecraft, didn't it? And that was how they found it, was because the spacecraft was in a different orientation.
Right.
So there is that, and there is in the works, and I don't know if it's still in the works or not, but there is another spacecraft that's gonna go out, that's gonna be in position so that it can spot the things that we can't see coming from the sun side. So I sent a letter to, all kinds of politicians to say that we need this.
That one made the cut in the last. I mean, the recommendation was that.
But I think NASA decided to put it on the back burner now.
Oh, I didn't know that. I guess the
It's NASA
National
that's causing
Academy,
it.
the National Academy of Sciences recommended.
Because it did get, you're right, it did get funded, but then NASA put it on the side burner.
Okay, not good news.
Last I heard.
But-
Anyway, the situation is, that is a blind spot, and we know it, and we get a spacecraft up there that can search that area around the sun without, causing too much trouble.
I think we should write another grant so we can put up our own scope.
Yeah.
And really do remote.
Put it up in space, yeah.
I got a garage if you want to build it, so.
Yeah.
you know.
Hey, it's 16-inch up in space will be awesome.
Yeah, yeah. There was actually an attempt to do an amateur space telescope one time. They even had built some of the electronics in the
It was
bus.
supposed to go up on the, there was something on the, and I haven't heard anything about it for a long, long time. There was something on the Space Lab, the
Oh, on the
Yeah,
space station?
ISS?
On the space station?
yes, on the SSS, SST. whatever.
This was something I
ISS.
just remember seeing an article about it in like Science News back in the 80s, and I don't know if it ever actually got launched, but.
I think, it seems like a 10-inch or something got put on
Okay.
the, that orbit.
Space station.
Space station.
Okay. Well, as always, if you find interesting news articles, I guess we're not going to be having anything real soon, but send them to me. I'm always interested in new stuff. Okay. Well, the last couple of meetings, I've kind of just done like stuff in the sky now, and I decided I was going to go back and do something that we used to do and kind of fell out of the habit of doing it. So let me know if you think this is better or not. But we used to do sort of focus on a constellation, and so I thought I'm going to do that this time. So the constellation that I chose to focus on is Perseus, and I chose it for a couple of really specific reasons. One of which is that it's becoming a more prominent constellation in the sky. It's kind of a winter, more easily seen in the wintertime, the northern hemisphere winter. So I thought I'd talk a little bit about the constellation Perseus. Well, anyway, as far as where Perseus actually is, there it is right there. It's kind of in the northeastern sky right now, if you're where we are. My little trick for finding it, and I'm sure people like Janelle, who are masters of knowing the sky, have much better ways of doing this. For me, my trick is I find Cassiopeia, which is always an easy one for me to find because it looks like a big sigma, right, or W, and I find the shallower side of it, right? It's got like a deep side and a shallow side. I find the shallower side. I connect the middle star of the shallow side with the middle star of the constellation, draw a line through them, and it essentially points at Perseus's head. So that's my trick for finding Perseus. So there it is right there. This is the constellation art for it, and in art, Perseus is usually shown as a warrior, basically as a soldier, carrying a severed head. And there's a story behind that relates to the mythology of all this. And that mythological story actually involves a lot of the constellations that are around Perseus as well. So there's this whole mythological tale kind of caught up in that. And if you look at the head, it's actually the head of the Medusa Gorgon. We'll talk about what that is here in just a second. One of the bright stars, actually the second brightest star in the constellation, is called the Demon Star, Algol. And it's the eyes of the severed head of the Medusa, Gorgon Medusa. So anyway, that's kind of that's where the mythological story of Perseus starts. So as far as the myth goes, Perseus was the son of a god and a mortal, right? It was the son of Zeus and Danae, who was the daughter of a king Acrisius of Argo. Argo is where the Argonauts were from, right? And the deal with King Acrisius was that at one point, even before Perseus was born, it was prophesied to him that his grandson would kill him. And so he became obviously very concerned about this. So his answer to that was to basically imprison his daughter, Danae, so she wouldn't have any opportunities, right, to have a child. This came to the attention of Zeus, who's also Jupiter in the Roman gods, who basically took pity on her, rescued her, and fathered her child, who was Perseus. When Acrisius found out about that, he decided he would get rid of the boy and the mother. So he basically enclosed him in a wooden box and threw him in the ocean. By the way, I'm not hugely I'm not a huge fan of mythology, but I kind of enjoy the mythology associated with the stars. One of the things I consistently notice is that parents in mythology are awful people. You know, so this kid, this king threw his daughter and his grandson in the ocean. They washed up on an island where they were taken in by a local fisherman, and who raised Perseus as his son. The fisherman's brother was the king of this island, King Polydectes. And King Polydectes apparently took a shine to Danae, took a shine to Perseus's mother. Perseus did not think well of this, wanted to kind of keep them apart. This king, who apparently was not a particularly brave man, decided that his solution to that is he would get rid of Perseus through subterfuge. So he basically set up a situation where Perseus would end up fighting this Gorgon Medusa, which is a Medusa is a mythical monster that if you look in its eyes, it'll turn you to stone, right? So Perseus ended up with the task of killing this Medusa Gorgon. The Medusa Gorgon was the queen of the Medusas, who were a group of kind of monsters, basically. So Perseus approached this problem by basically taking his shield and using it as a mirror. So he held it up, and so he could sight in on the Medusa Gorgon without looking it in the eyes, caught her sleeping, smacked the head off, stuck the head in this bag, and went back to, headed back to kind of show that to Polydectes and you leave my mother alone. On the way, and there's two things that Perseus was sort of famous for. One of them was killing the Medusa Gorgon. The other one was rescuing Andromeda, who was the daughter of Cepheus and, drawing a blank here. The W constellation.
Cassiopeia.
Cassiopeia. God, yes. She was the daughter of those two, and they were also not very good parents. And Cassiopeia was a very vain woman. She's usually shown in mythology looking at herself in a mirror. And she bragged at one point that she was more beautiful than the sea nymphs, who were Poseidon's favorite children, and Poseidon did not take well to that. So he sent this monster, this sea monster, Cetus, to terrorize the kingdom. And this, I believe, was in Ethiopia. And so in order to get rid of this thing, the king here, Cepheus, chained Andromeda to a rock. And the idea was that the sea monster would come along and take Andromeda, and that would settle the score, right? So Perseus came along and found Andromeda chained to the rock. He was on his way back with the severed head at the time, released her, freed her, and they ended up eventually falling in love and being married. But so those are the two things that Perseus is kind of best known for. This painting right here kind of shows both of them. There he is with the head, and he's about ready to free.
Is he pointing the head at the sea monster?
I don't know exactly what it is that he's doing there.
Multitasking.
Yeah, he may, but at any rate, he saved Andromeda, and also got back with the severed head, took it out of the bag, showed it to Polydectes, who turned to stone, and apparently that was the happy ending of the story. The bad guy turns to stone, and mom is safe. Apparently, eventually, Perseus went back to Argos, and where his grandfather was the king, and he, or at least the father of his mother, I guess that's his grandfather, and he was participating in a track meet, I guess, a field event. He was throwing the discus, right? And of course, he was a really good discus thrower because he was a big, brawny man. And he whipped the discus, hit the king, and killed him. So the prophecy turned out to be true. He did, in fact, kill his grandfather. Not in the circumstances you might think, but anyway. So that's the myth of Perseus. And if you kind of look at the area of the sky where Perseus is, right, there it is right there, you can kind of see some of the characters. There's Cassiopeia. She's often, as I said, depicted as a woman looking at herself in the mirror. There's King Cepheus, who, you know, was not a particularly kind man, apparently, if he's going to sacrifice his own daughter. There's Andromeda right there, very large constellation, a great square right there. There's the monster right there, Cetus, that's the whale. So these are, you know, all these characters are kind of in the same area of the sky. So anyway, that's the story of Cepheus. As far as what to see in this, and the reason why I chose this one, the number one reason is that it's the Perseids. And the Perseids are actually active right now, and it's a good year for them. I haven't really seen any of them myself, but it's an exceptionally good year to see these. And I'm kind of a sucker for anything that involves meteors, right? So this immediately attracted my attention. So the Perseids, the radiant form, the Perseids are the remnant of a comet Tempel-Tuttle, I believe, which is a relatively short period comet, maybe around 40 years, I think. Yeah. And so it's been through the solar system a number of times, right? And it's left a lot of stuff behind as it's passed through. So there's a lot of material that can form these meteors. So I think the prediction this year was about 15 per hour, which is quite a few. So if you want to see the Perseids, the radiant is kind of right next to Perseus's head, right about there. So again, my favorite landmark, or one of my favorite landmarks, is always Cassiopeia. So go to the end, go down, and that's about where the radiant of this would be. Okay, so that's one.
Unfortunately, at Farpoint, that's looking towards Topeka.
Yeah, it's kind of lost in the glare. Yeah.
But keep in mind, later on in the night, when that rotates around, then it becomes a lot better. So, and you get better, usually get better asteroids in the morning rather than the evening.
Yeah, yeah. And in fact, this
Or meteors, sorry.
this image right here is actually kind of. This image right here was actually I got this off of the planetarium. This would have been what the sky looked like at about 7 o'clock tonight in Manhattan. So it'd be pretty similar to what you would see here. But again, yeah, looking off to the north, especially from Farpoint's going to be looking back into the Topeka lights.
Keep in mind also that the brighter ones generally are further away from where the start point is anyway.
Mm-hmm.
So basically all over the sky is good viewing. So you're not really looking at the radiant generally, because the radiant is where they start from.
Mm-hmm.
They usually don't get bright until they get away from that radiant.
And I think the Perseids are one of the ones that kind of tend to look a little greenish, right? They're heavy and
Heavy and iron then?
Yeah, maybe, or maybe I'm confusing them with a different one. But anyway, good chance to see if you want to brave the cold, a good chance to see a nice meteor shower. Okay, so that's the focus constellation for this month. Again, if you have a suggestion, please let me know. If you got a constellation you're interested in, let me know. They almost all have a pretty interesting story behind them, and they almost all have interesting stuff in them. So here's one of the things I think is most interesting in Perseus. This is that star that I talked about that's kind of the eye of the Medusa Gorgon in the depiction. It's called Algol. Also sometimes referred to as the demon star, largely because of its association with that Gorgon, but also because it was one of the very first variable stars ever identified, and it's one that the variation in it is really obvious even to the naked eye. It varies on a very short time period, about 2.867 days, which works out to 2 days, 20 hours, 49 minutes. So every 2.89867 days, it gets dimmer for about 10 hours, and it's very precise in its timing right now. So it's actually a triple star system, a binary and then another one. And one of the other things that's kind of unusual about Algol is, in fact, it's sometimes called the Algol paradox. I remember learning this in an astronomy class way back when, is that typically you would expect that, a double star system usually has a larger component and a smaller component. And the larger component is usually the older one, the one that's further along in its evolution, because it's more massive, and the more massive a star is, the faster it ages, basically. But in this case, that's not true. The smaller one is actually the apparently older star. And it's kind of this paradox that I don't think anybody has totally explained yet. One characteristic of these, and this is actually the prototype of what are called algol variables. They're a type of variable star that's really close, and both stars have kind of reached their Roche lobe, basically. They're kind of oblong in shape. And they probably are exchanging material between them. So one of the theories is that there's been an exchange of material, that essentially the larger component is drawing material from the smaller one, and that makes it look younger or something like that. I don't know, it's like a vampire kind of living off the young. But at any rate, as far as I know, this has never totally been explained. But it kind of shows you that even really familiar stars can really have some mystery associated with them. It's the very first star that was ever, or very first double star, variable star that was ever analyzed spectroscopically, and it was the very first one that was ever measured photometrically. The guy that measured it photometrically was a guy by the name of Joel Stebbins, who at the time was at the University of Illinois. This was in, I believe, about 1908. And when I was a student in Illinois, my building was right next door to the observatory that he worked at. Of course, he's long gone, but I always thought that historical interest, that always kind of caught my historical interest, that this, kind of milestone really in astronomical research was carried out in the right next door. I could look out the window of my office and see this observatory. So anyway, there's the light curve of algol. This is kind of what it looks like. So that's at 2.867 day. And so every 2.867 days, it gets dim for about much dimmer, visibly dimmer. If you watch it, you can see this easily.
It's about twice the brightness.
Yeah, and I mean, it is obvious that it's different. For about 10 hours, then it brightens up. And that's the period when the little one has passed in front of the big one, right? The smaller component is in front of the bigger one. And then when the opposite happens, when the smaller component is behind the larger one, there's a slight dimming. So that's what this would be right here. And so this pattern of big dim, slight dim, big dim, slight dim is diagnostic of an algol type variable. This is kind of burned into my memory because I got a question about this wrong on an exam once. So I will never forget now that what the light curve of an algol looks like. But anyway, that's one of the more interesting objects, I think, in it. It's this star right here. It's not the brightest one. It's actually the second brightest one in the constellation. The brightest one is called Mirfak, and it means elbow. So that's Perseus's elbow there, basically.
Les said something.
Oh, Janelle said the Leonid's peak is tonight.
Okay, so Leonids are peaking tonight? Okay, and that's in a different part of the sky, right?
Guessing
Yes.
Leonid.
Leonid is Leo, so
Uh-huh.
that's
Yeah.
Leo's where the center is.
Mm-hmm. Anyway,
Back, gosh, how many years ago has it been? Probably a dozen years ago. Out at Far Point, we had a really good night for the Leonids, and it was spectacular. It was, you could see one about every 30 seconds.
wow,
And the bright ones, really lit up the sky.
yeah.
So that was quite an experience for those that were out there.
And where is Leo now?
In the early morning, it's still to the east, so it's
Okay.
it's at about 10 hours right ascension. So right now, we're about 22
Uh-huh.
overhead, so we tell it's a long way into the morning before you get to Leo.
Okay, all right.
So it rises up pretty late, but the problem is, at 2 or 3 o'clock in the morning, it's about maybe 20 or 30 degrees up, but that produces a shower to the west, so you still get a good view.
Okay. Other stuff?
That's the reason why it's cloudy tonight.
Yeah. Other stuff you can see, a couple of Messier objects, M34, which is a kind of an open cluster. It's one of, I think, only about 4 clusters that's in that are in the Messier catalog. It's also, I think the story I've heard is that it's actually probably related to the Pleiades, that there may have been formed in the same kind of in roughly the same place, and they're very similar stars. So they're real young. They're real blue, and I think this this object I think you can sometimes see with the naked eye if you've got a good eyesight and it's a clear night. This is M76, called the Little Dumbbell sometimes. This is a planetary nebula. And what's kind of interesting about this one is that it actually has two entries in the NGC catalog, because the thinking now is that it's really two objects. It's two different nebula that just happen to be kind of close to one another. So this is another object that's in Perseus. This is one I think is pretty hard to see with the naked eye, but I see a lot of good photos of it, so it must be a real, kind of plum thing for astrophotographers. This is the California
It's
nebula.
like 3 degrees wide, so it's pretty big.
Pretty big, yeah. It, I guess if you squint your eyes enough and kind of use your imagination, it does kind of look a little bit like California, but only a little bit.
You can see the San Andreas Fault.
Yeah, you can see. In San Francisco would be a water mountain right there, I guess. Los Angeles would be down here somewhere. But anyway, San Diego, Anyway, that's, you can kind of see where it is here. That's, it's, as like I said, it's a pretty big object, but apparently very hard to see with the naked eye. So, popular with astrophotographers, though, apparently. And this is the one that really just blows my mind. One of the things that's in Perseus is the so-called Perseus supercluster, or sometimes it's the Perseus-Pisces supercluster. And this is a cluster of galaxies. This is the largest known structure in the universe, as far as I know. It's basically just a huge number of galaxies that are sort of bound together by mutual gravitational attraction and possibly something else not entirely well understood.
Arcturian chain.
Yeah. And it's just enormous. It covers, I think, something like 40 degrees of the sky. Sometimes you'll see those deep field, you'll occasionally see deep field images where every spot on it is a galaxy. There's no stars. Those are usually shot in this supercluster. So there's places you can look in this thing where everything you see is a galaxy. And just the idea of something that big is just kind of amazing to me. So cosmologists actually have a name for this thing, and I can't, other than the.
What'd you say?
I was thinking Arcturian chain, but that's not right.
It's like a Hawaiian sounding name, because the guy that named it was at the University of Hawaii. I'll have to look that up. But anyway, this is, I think, just a kind of one of those astonishing things that there's this absolutely huge structure out there. Anyway, so that's a deep sky object that you can see in Perseus. Okay, so anything else?
I forgot my calculator.
Okay, well, there will be no math. There will be a quiz at the end of this, though, so make sure that you're, take copious notes. So what I wanted to talk about tonight was the Drake equation, which is, and what kind of inspired me to talk about this, or maybe kind of think to talk about this, was that its developer, Frank Drake, died not that long ago. He died at the beginning of September. So it kind of brought the Drake equation back into my attention. So I thought I would do a little bit of a presentation on it. So there's Frank Drake, died in September. In the Drake equation, one of the interesting things about it is it's, some people think, the second most recognized equation in science. Probably the most recognized one is the Einsteinian equation, right? Equals mc squared. People think the Drake equation is the second one. Actually, penetrates, it's one of the very few equations that penetrated into the popular culture. You can buy t-shirts with it on there. It's been parodied on on the Big Bang Theory. There was a episode where apparently they discussed the Drake equation. So, a popular TV show assumes that their readership or their viewership is going to know what this thing is. This is a children's book, or a young adult reader book, the Jamie Drake equation. This is apparently the story of a kid whose father is an astronaut and gets stuck in space, and Jamie has to somehow figure out how to rescue him or something, according to the description I saw on Amazon. But I thought this was just really interesting. And here's another parody. This is the Flake equation, which has to do with people who believe in alien civilizations or something like that. But it's another parody, I guess you could say. So this is kind of penetrated into the popular culture a little bit. But if you start looking at it and its history, it turns out to be really, really interesting. And Frank Drake's role in all this, really interesting as well. And the roots of the Drake equation actually go back to kind of the late 50s, early 60s, when scientists were beginning to seriously think about, is there life out there? Is there intelligent life out there? If there is, how do we figure it out? And it was not the sort of thing you probably wanted to say out loud back in the late 50s or early 60s. I mean, SETI was nowhere near, you know, it wasn't even on the radar, no pun intended, at that time. But one of the people that decided to kind of take a crack at this was Frank Drake. And he later said that, you know, he was just too dumb to realize that this was dangerous for his career to kind of get off onto this weirdness. So he instituted this thing called Project Ozma, where he and some colleagues monitored 2 stars at wavelengths around 21 centimeters. Of course, that's the wavelength of hydrogen, neutral hydrogen, right? So it's considered to be one of the places that a signal might be hidden. And of course, they didn't really find anything, but it got people thinking. And there was a subsequent follow-on where they looked at even more stars. Still didn't find anything, but the idea kind of began to penetrate into the mainstream just a little bit more. One of the people that kind of got wind of that was Carl Sagan, who was a graduate student at that time at the University of Chicago, but already kind of making a name for himself as a very ambitious go-getter kind of character. He went and contacted Frank Drake, and they started a collaboration that lasted throughout both of their lives, basically. And it also kind of came to the attention of the National Academy of Sciences. And the National Academy of Sciences decided that they needed to have some sort of a workshop to talk about this. And this is really where the Drake equation came from. It came from this workshop held in 1961 at the National Radio Observatory, which is in Green Bank, West Virginia. It wasn't a very big conference. There was only, I think, 11 people there. But the people that were there were major heavy hitters in many different fields of science. So Frank was there, Carl Sagan was there, still a kid at that time. Probably wasn't even 25 yet. Philip Morrison, who wrote the first paper suggesting that you might search for alien civilizations by listening. This guy was Melvin Calvin. During this meeting, it was announced that he had won the Nobel Prize for figuring out how photosynthesis works, basically. So, these were top drawer people, just, brilliant people. And this guy right here became sort of the star of the show, though. This is a guy named Lilly. And the reason why he got invited to this was he was actually trying to talk to dolphins or communicate with dolphins, basically. And people were so enamored of this idea at this meeting that they created this thing called the Order of the Dolphin, which is still kind of extant in the SETI community. People are inducted into the Order of the Dolphin, but these were the original ones. Lilly's work has kind of been a little bit discredited since then. I think he kind of went a little bit off the rails, to be honest with you. He began experimenting with drugs as a way of kind of heightening his senses, and isolation tanks and things like that. And I think he got a little off the beam there, but they took him pretty seriously at this conference. There's actually been 2 movies made about this, roughly based on this guy's life. One of them was called Altered States, and the other one was called Day of the Dolphin.
Altered States.
Yeah, Altered States is a pretty good movie, actually.
Yeah,
it's not about dolphins, but it's a really good movie.
It's,
But anyway, this and the thing that happened, in order to organize this conference, they figured they needed some kind of framework. And Frank Drake suggested that framework by writing this relationship literally up on the blackboard that might kind of help understand how many communicating civilizations there might be. At that time, they were thinking about it in the Milky Way galaxy. They were confining themselves to one galaxy. And that became the Drake equation. The way they actually organized this was a 7-day conference. So every day they talked about a different term in this and kind of considered what the values of these would be. So the Drake equation then tells us the number of civilizations, or it purports to tell us the number of civilizations. And you can see it's the product of a bunch of terms, right? All these terms are either numbers or fractions. So R star is the rate at which stars are born. F sub p is the fraction of stars that have planets. N sub e is the number of those planets that are habitable. F sub I, which is a fraction, right, a number between 0 and 1, is the number of those planets on which life occurs. F sub I is the fraction of those that involve intelligence. F sub c is the fraction of those that become communicative. They can actually communicate across space. And then finally, L is the average length of time that those civilizations would be detectable. So what they did at this conference is they talked about these ideas. And of course, back in 1961, there wasn't a whole lot of hard information about anything. So kind of still isn't, to be honest with you. A little better now, but 1961, nobody really knew much at all about this stuff. So a lot of what they talked about was pretty speculative. One of the things I didn't realize about the Drake equation until I started doing a little bit of research for this presentation is the terms are actually presented in a descending order of certainty, at least as it was understood back in 1961. So R star was considered the most certain thing. It was actually fairly well known even then, how the rate at which stars form. And as you go down the list, these become less and less certain until finally you come to the one that's kind of the real bugaboo in all this, which is the L term, how long a civilization will actually last, basically. And so they kind of talked a lot about this stuff, and eventually they kind of came up with what they considered to be at least some reasonable estimates for these things. So they figured R star was about 1. There's about 1 new star formed every year. And that's actually not too far up from what current estimates are. They thought that about anywhere from a fifth to a half of all those stars would have planets. This is actually something that we can get a little better handle on now because we're starting to see planets, right? About 1 to 5 of those would be in the habitable zone. They figured every one planet in the habitable zone would develop life. They figured 100%. Every planet that had developed life would develop intelligent life, and that was based largely on what was understood about evolution at that time. And then about 10 to 20% of those would be able to communicate, that FC term. Where they really got most speculative was that last term, though, and it must have been, I would have loved to have been a fly on the wall when these guys talked about this stuff, because it would have been really interesting to hear these, just brilliant people speculating, right? Thinking wild. But they decided that number had to be somewhere between 1,000 and 100 million. That is a big range, right? That's like 5 orders of magnitude of range. So based on all this, and particularly considering this huge range of L, they decided that in 1961, if they considered the absolute low end of these, took all the low values down this, there'd be about 20 civilizations in the Milky Way. If they took all the high end, there'd be 50 million. So the range of values that they came up with was somewhere between 20 and 50 million. And not 20 million and 50 million, 20 and 50 million. So,
Too much beer.
yeah, boy, that must have been a fun conference, though. Boy, that would have been fun, But anyway, so uncertainty with L has always been one of the major kind of issues with the Drake equation. And of course, like a lot of things, it didn't sit still. It kind of took on a life of its own. Lots of other people tried to figure out what these values might be. Many people took a shot at this. It was kind of funny if you look at various disciplines. Biologists tend to think life is really rare, but there was tons and tons of planets. Astronomers tended to think maybe there's not that many planets, but boy, life must be everywhere, right? So, the mutual ignorance there kind of drove a little bit of that. But at any rate, this was another source I found that, again, kind of shows this huge disparity that's possible if some of these numbers are uncertain. So this was a study they did that was purported, it was by a group of biologists, purported to show how rare a planet like Earth might actually be. So they took pessimistic and optimistic values. They used a pretty high rate of star formation. Again, these were biologists. This number's probably 2.5 times too big. Fractions with planets, they thought, they were very optimistic about that, 80 to 100%, right? Data may be suggesting that, hey, they were right about that one. But what was really interesting was length of time. They considered 100 years to 10,000 years. And based on that, N was somewhere between 0.014, and we know for sure that number's too low, right? It has to be at least 1, because us.
Right.
So that number's obviously too low, and 140,000. So their conclusion was that, you know, the crazy people at Green Bank.
I would disagree with your statement. The total number of civilizations in the Milky Way galaxy right now, there's right now, meaning our time frame, or 1,000,000 years from now, because I'm not sure our civilization will be there 1,000,000 years from now. So if you take it across the whole time spectrum, and any point along that, there may be 0.014.
Yeah, I guess that's true. Also, it may be that we are really not one of the civilizations that would show up in all this for a reason I'll get to here in just a second. We may not actually be eligible to be detected by.
Let's say, did they define intelligent life or civilization?
Well, and that's
Yeah,
that's the other thing is there really intelligent life here on Earth? But I like to think so. Maybe I'm too optimistic. But anyway, this kind of what this is kind of shows is that there's a lot of range in these things, and a lot of times the estimates are kind of biased by who it is that's doing the estimating. So I thought I'd just look at each term here and kind of maybe give a little idea about what the current thinking is on these. And again, this is based on me doing very little research, so there may be, I may be missing things entirely here. But, so the R-star term is the one that's probably best understood. There's been some pretty good studies of this done. You can calculate this by looking at changes in the mass of molecular clouds, because you figure that molecular clouds are turning into stars, right? You can do it by direct observation, just seeing how many real young stars there are out there. And this one down here is probably the one that is most recent. You can compare the ratios of young and old stars, and that might give you some idea of the rate at which they're being created. And generally speaking, the range of values is somewhere between 0.56 and 7 based on this per year, with the best value between about 1.5 and 3. And that doesn't necessarily mean that, every year 3 new stars form. It probably means that, they're coming in batches, and then there's a long break, and then another batch, and so on. Also, the idea that they're going to show up in a year seems a little odd to me. I mean, I don't know that much about stellar evolution, but they don't just form overnight, right? It takes a little bit of time. So, but anyway, that's based on some of these studies. That's the considered one to be one of the best. And that's really not far at all off what the Green Bank people said. They said 1, I believe. So it's pretty close, comparable. The fraction that of the FSOP fraction, the fraction that of those planets that, or the fraction of those stars that have planets, is one of those things that current research can actually kind of inform. We know a lot more now than they did back then because of studies of exoplanets, right? So we're finding these systems that have planets around them and understanding the characteristics of those a little better. So the original Green Bank estimate was between 20% and 50%. Current estimates are right there with the biologists, 1. Their current thinking is that every star has planets. Again, I don't know. I mean, my understanding of it is not that good, but this is what some of the current thinking is. The fraction of those that are basically kind of eligible for life, that are kind of in that habitable zone, is a little bit harder to get a handle on. But here again, this may be a place where some of the exoplanet work kind of informs this. So I did a quick back of the envelope calculation based on almost no data whatsoever from the Kepler thing, which of course Kepler was a satellite that's no longer functioning, but what it did was stare at one spot out in the space for a very long period of time and it was measured transits, right? It measured brightening and dimming of the stars as a way of understanding planets passing in front of them. So about 2,600 exoplanet discoveries. I think that number's actually a little low, but it was one of the numbers I found. 47 of them were in the so-called habitable zone. That's basically the zone where liquid water can be found. About 8 of those were similar in size to Earth. So if you want to confine your analysis to Earth-like planets, that suggested a value somewhere between 0.003 and 0.018, which is not a very big number, right? I was surprised by how small that number was. Of course, this is me doing very literal back of the envelope calculation. I had an envelope on my desk that I wrote the numbers down on. This is another analysis, probably much better because it was done by actual scientists in this area. Again with Kepler. This was published in the Proceedings of the National Academy of Science, which is a very prestigious journal, so it probably got a lot of scrutiny. Prevalence of Earth-sized planets orbiting sun-like stars. The diagram here is a little bit cryptic, but what this basically tells us is if you look at Earth-sized planets, right, 1 Earth radius, with orbital periods somewhat similar to ours out here in the periods of hundreds of days, these are the numbers, the proportions of the Kepler detections that fall into those categories there. So if you add up all these numbers, it comes out to about 0.4. That's a little bit less than the really optimistic numbers that others have been using. Probably a little bit more.
I wonder how they considered the bias here, because obviously the bias is going to point towards stars that have planets that go in front of them much faster, therefore much closer, and therefore that skews the data. And I wonder how much they accounted for that.
Yeah, and I mean, that's exactly right. For one thing, it can only detect transiting planets, right? Mm-hmm. So if the planet is orbiting some way that it doesn't pass in front from our view, right? If it's going that way, you're not going to be able to detect it. And the exoplanet detections are still heavily skewed toward big things that are close to their star, because those are the ones that pass in front of it more often. So yeah, so this is biased towards things that would not be Earth-like. So yeah, this number may be a little bit low if you think about all those biases, but it certainly, I think, gives you at least a ballpark. It's at least an attempt to use data. It's not just kind of waving our hands.
And certainly they took that into account, I would guess. I mean, they wouldn't have missed that, I don't think.
Yeah. But anyway, I haven't looked at this article yet, but it's on my list of things to read when I get time. So I'm thinking sometime in about 2035, I'll get around to this one. But anyway, but this again, what I thought was noteworthy here is that this is actually based on analysis. It's not just like, oh, I think it's 1 or I think it's 0.2. Anyway. So some of those other fractions, the fraction of planets that are Earth-like that produce life, and then the fraction of those that produce intelligence, and then the fraction of those that communicate, this is really where they start to get into some even more speculative stuff. But we can kind of get at least an idea about this by looking at potentially habitable things in our backyard, right? So we know that Earth obviously is more than just potentially habitable, it's habitable. So it gives us an idea of what to look for, right? We can understand based on the case of Earth that if you want to find a planet with life on it, one of the clues is you look at its atmosphere, right? And if the atmospheric composition is stuff that can't, it can't be there without some sort of disequilibrating process, then that's kind of a clue, right? That's a way you could detect life on Earth. There's some other places, Enceladus, which we looked at earlier, now is even more likely according to that study that we looked at earlier. So that might be a possible abode of life. Europa, kind of the same. It's got this interior ocean, right? Mars, probably not very hospitable to life now, but there still may be some remnants of life from an earlier time when Mars had a lot of water on it. So all of these are potentially habitable places in our solar system. And if even one of these turned out to have life, then I think that would have some pretty major implications, right? It might suggest that FL number really is one. That, if the if the conditions for life are present, life will evolve. Again, one of the ways that you can kind of detect all this would be looking at atmospheric compositions, and the James Webb Space Telescope is actually, that's one of its missions, right, is to be able to analyze the atmospheres of exoplanets. So here on Earth, if all this stuff in the atmosphere kind of points to something that's basically or continually disturbing the atmosphere. If there wasn't life, it would basically kind of default to carbon dioxide or something like that. Even in the early Earth, this would have been the composition of the Earth's atmosphere at earlier times, after the evolution of life, but before now. It would still, you'd have these nitrogen and methane and things that would be kind of biosignatures, right, bioindicators of life. So this is something that I think astronomers are pretty keenly interested in, because this could be super important evidence that there's life out there. And this might actually inform estimates of how many places there are. The intelligence one is a little bit harder to get a handle on, but I did see one study that tried to use a statistical approach to doing this. So this gets a little involved. It basically involves what's called Bayesian analysis, which Bayesian statistics are just a way of thinking about statistical processes if you think you know something about the answer. So if you're trying to model a Bayesian process of say flipping a coin, there's a baseline probability of 0.5, right? So you can kind of use, it's called a prior, and you can kind of use that. So some biologists again, decided to use data about, or tried to use understanding of evolutionary transits here on Earth as Bayesian priors to try to estimate what the possibility of life was. And so they, all these transitions from abiogenesis to biological activity, to more complex cells, to sexual reproduction, and finally intelligence, going back through time from present basically back to about 4.1 billion years ago. And the kind of outcome of all this was that they figured it was a really, really low probability that intelligent life would form. This was probably the most pessimistic thing I saw. Their estimate, incorporated into somewhat optimistic values of the other terms, still suggested less than one intelligent civilization per galaxy, basically. So this was the only attempt I could see to really try to do some actual analysis of this. The communicative intelligence one is a little bit difficult too, because what we're talking about here is basically how long a civilization might last, right? And we don't really have very good ideas about that. This is actually one of the things that there's been a lot of speculation of. Some people have suggested that that the time limit for communication is very short, that any civilization that reaches a level of technology that will allow it to destroy itself will. And that's a pretty pessimistic way of looking at things, but that's what some have assumed. So we have had the capability of destroying ourselves for about 70 years now, maybe. So I don't know where that leaves us as far as where we stand on all this. But this little calculator right here is kind of fun to play with, because it can let you kind of save these. But what I thought was interesting was that the skeptical range on this, the length of time that signals could be sent in space, was 10,000 years. So that, that's considerably more than some people have thought. But if you go to this site here, you can actually kind of play around with the terms and see. Even the skeptical thing was pretty optimistic. The lowest possible would be, I think, 0 in this case, which obviously would make the whole thing equal 0. So anyway,
one more term that probably, I don't know if it's really in there or not, but one more term that you could think of, and that is when our civilization is going to be viable and can send communication at the same time somebody else is, and and
that may be out of sync too.
Yeah.
So this is the biggest unknown in the whole thing, and one of the ones that produces probably some of the most hardy discussions, because there are people that think essentially that any technologically capable society is going to basically destroy itself. This was probably the biggest unknown back in the Greenbelt days as well, or Greenbank days as well. But here's one of the things that I thought that was kind of interesting when I was doing all this. There's been this idea of the great filter, right? So Fermi's paradox, which is kind of closely related to all this, basically is why, if the universe is full of civilizations, why haven't we ever contacted them? There should be all over the place out there. This was Enrico Fermi who kind of came up to this. Apparently he was in casual conversation with a friend of his and proposed this paradox even before all the Drake equation stuff. And it's kind of a fair question, really. So the idea is that there's this thing that they call the great filter. So, you get some of those other terms, right? Life develops, life becomes technologically capable, and so on. But that eventually kind of hits a wall. If it can make it through this great filter, then it can become one of these civilizations that might be detectable. So a type 1 civilization is one that can use all the energy on its planet. Type 2 is one that can use all the energy available in its solar system. And a 3, I believe, is all the ones in the star, or something like that. But anyway, these would be detectable civilizations. So under this scenario, we aren't yet. We would have not reached type 1. So even though we've probably been sending detectable radio signals out into space for maybe 90 years or so, or 50, depending on kind of how you look at it, we're still not in that window of detectability. So this is us. We're approaching the great filter, and some civilizations make it through here, some don't. So that's kind of the idea here. But it sort of gets to that notion of, maybe these things come into existence, but maybe they're so rare that there's never more than one at a time, right?
It seems that the distance between two civilizations is an important factor.
Right, because
It's
signals
kind of
only
like
travel
Gary's
so
saying the
fast.
time, but it takes a while for a signal to get to someone that we're talking about.
Yeah.
So
You got a 10,000-year lifespan, and it takes 5,000 years to get a message there.
or longer.
You're done.
Yeah.
Right. So yeah, it could be that, there's this brief window, signals go out, and then no more. Anyway, this was, I thought, kind of an interesting take on that problem of L. This was another interesting take on it. This is actually by an article that was in Scientific American, Why E.T. Hasn't Called. And this was actually, again, one of these analyses that somebody kind of did in their spare time, I think. This was a guy by the name of Michael Shermer. And what he did was look at civilizations on Earth as kind of analogs, right? So he examined 69 civilizations here on Earth. 29 of those would be considered technological civilizations. He found the mean life of any of them were about 421 years, and the mean life of a technological one was only about 305 years. And based on all that, he came up with an N using some other parameters of about 3.5. The thing about this one, though, is that these civilizations were things like the Maya civilization, right, the Egyptian civilization. They were not global. And so it could be that, the continual presence of civilization, if you want to define it that way, is much, much longer than this. So I found this, I don't know, not very compelling, but at least it was another attempt to kind of try to put some numbers on all of this. All right, so I guess one of the questions I kind of wanted to set out with here is this really useful? And does it need to be rethought a little bit? And as you can probably guess, people have been rethinking this since probably it was first written down. And one of the more interesting attempts at that, I think, was an attempt to simplify all this, basically. So this was an idea that there was too many terms, right? But you can kind of group some of the terms together. So you can group together the R star and the F sub P and maybe the N sub E, which are things that maybe we're starting to get some real data for, and just call it what they call N, the number of habitable planets in a given volume. So you define a volume, there's going to be a number of habitable planets in it. And then you multiply that by the likelihood of a technological species arriving, which is kind of the product of these three really unknown fractions times this L. So this really kind of vastly simplifies all of this. I can see the point of what they were trying to do here, but one of the things I think is really useful about the Drake equation isn't just that it, is this method of estimating how many civilizations there are, because to be honest with you, I don't know if that's really all that helpful. But in thinking about this, I'm always kind of guided by this quote right here. This is George Box, who was a very well-known statistician, basically. If you ever took a statistics class and you did the Box-Cox test, this is the guy that invented that, or co-invented that. And he used to say all models are wrong, but some models are useful. And as a person that uses models quite a bit in my research, and a lot of what I do is aimed at kind of informing models, I've always kind of been really kind of interested in this thought. And so something, and based on that, I tend to kind of look on something like the Drake equation as a model, right? It's not really an equation in the typical sense of the word, right? It's more like a model, a conceptual model. And using it as a conceptual model provides an organizing framework, which I think is what Drake was originally trying to do. That was his purpose. I don't think he was really setting out to say there's this many civilizations or there's a number between this and this. I think what he was really trying to do was start a conversation and give that conversation a context to take place in. And I think that's really what the great contribution of the Drake equation is. It's that it started a conversation that's 62 years later is still going strong and still being contributed to, and people are still interested in it. So I think that's really kind of the legacy of the Drake equation. So with that, I will stop.
Yeah, I like that. Being a high school math teacher, we're trained to think that anything with an equal sign
It's an equation.
is true.
Yeah.
Because at that level of math, it's all based on proofs and it's a real thing. But an equation that represents a model, very few people are exposed to that kind of thinking.
Right. Yeah.
So it's interesting.
And it's always difficult to get, I find, difficult to get people to think in terms of probabilities.
Mhm.
My previous life, before I did this, I was for a very brief period of time weather man. And it was always hard to get people to understand how weather forecasts work, right? That when you say there's a 70% chance it's going to rain, you're also saying there's a 30% chance it isn't. And it could be that it doesn't rain and your forecast was right because it hit in that 30%. And that's a concept that's hard to grasp, I think, if you're not used to thinking in terms of probabilities. So yeah, I agree. It's really difficult to kind of wrap your head around this kind of thing. And it's so deceptively simple looking, right? I mean, you basically write what you think are some plausible numbers down, multiply them by each other, there's a number. And so, yeah.
That was good.
Yep.
Other questions?
And
Okay.
NASA didn't they release it? It hasn't been peer reviewed yet. I printed out, I haven't read it, but there's a report from NASA on how that it looks like basically civilizations don't last. It was a pessimistic report.
Oh,
It just
yeah.
came out. It hasn't been peer reviewed yet.
Maybe I saw that one.
I think
Yeah, I mean, there's a lot of pessimism in that. If you ever watch the original Cosmos series, the one where Carl Sagan was the host, he talks about, directly and indirectly about this, and I think Carl was a bit of a pessimist, to be honest with you. He thought that, civilizations probably didn't last. But
Did Carl Sagan talk that way when he was younger? Because I
I was
think he's
thinking about
only
that.
really kind of famous for because of his voice.
Well, he did give a talk to the American Psychiatric Association, which was interesting.
He was supposed to give a talk at one of the Landon lectures at K-State, and I was really looking forward to seeing him, but by that time he had gotten ill, and he had to cancel the talk because his cancer did not allow him to, and he died very shortly after that. So I was always kind of bummed out. I never got a chance to hear him speak.
Janelle said good point.
Okay.
On what?
Your math thing.
Is there questions
I
on?
said something. Is your power cord working? I couldn't get it.
Yeah, he plugged it in. It was unplugged downstairs.
Actually,
Oh,
at
okay.
Washburn, we have a whole course in physics. Brian Thomas had a whole course. It was titled the Drake equation.
Oh, really?
It was a whole semester course, and we systematically went through every aspect of
That would be pretty cool. I would take that class. Yeah. I'm sure that there's all kinds of stuff that, like I said, this
it. That
was
was around the time, I think, it was a number of years ago when Kepler was launched.
okay.
And we were just getting information on
That'd be a really interesting, that'd be a really
Brian Thomas has got to have
interesting.
a pessimistic view because a lot of his study has been how Earth's gonna die.
Yeah.
I mean, it's,
Oh, with the
yeah.
radiation and the trees.
Yeah, that's right, that's right.
Right.
He's making predictions that
Yeah.
civilizations don't last long and something's gonna kill us.
Right.
Well, and that's the other, we
Magnetar comes along and you're done.
we tend to think about that in terms of, we will kill ourselves, but
Yeah,
there's a non-trivial chance that we'll
Yeah,
get hit with
that's
something
right.
pretty big, and it may not necessarily cause an extinction event, but it would certainly
Slow
put an
things down
end
a
to a
lot.
civilization,
Yeah.
at
We're
least
so
for a
dependent
while.
on our sun as
Yeah.
being stable.
Climate change could
Right.
kind of throw us a pretty big wrench too. So yeah, there's all kinds of things that can happen that don't involve, nuclear suicide. But
So given the definition of civilization like Mayans or Roman or those examples you gave, how many civilizations exist now on Earth?
I would say now it's just one.
It's
It's a
just one.
global civilization.
That's what I was thinking, but
And that was the-
back then, was it the distance between them that said that's a civilization and that's a civilization? Because right now, it's almost like that's countries
Yeah.
for
Well,
us
probably
now.
the evolution of what the from the Stone Age to medieval
Technology
times. Yeah,
changes.
technology. That's what I'm trying to say.
Yeah. Well, that was actually the objection I kind of had to that article that Michael Shermer wrote, the one about, why hasn't ET called, was he seemed to be kind of making a false equivalence between, these civilizations that occurred in ancient times that we know about archaeologically, right? Limited geographical extent, limited time span, obviously, and one that might be, a global civilization. I don't know, some of those must have been in business at the same time, right? I mean, it wasn't like one popped up and went away and then another one popped up and went
He
away.
wrote an interesting book, Why People Believe Weird Things.
Yeah, I've read that
And
book.
he lectured at Washburn,
Did he?
yeah.
Yeah,
He
he's
came to our
an,
atheist meeting too, I think.
he's an interesting character. He actually is a editor of a magazine called Skeptic, and
Yeah.
he's like the president of the American Skeptical Society, which is a wonderful
We
name.
went to, after his lecture at Washburn, we went to the observatory, and Brian Thomas was there, and we looked through the scope, we were aiming towards, I think, Jupiter, and we
Mm.
couldn't see anything. And you know what happened?
Yeah.
Brian forgot to take the lens cap off. We had to turn the whole scope around
Oops.
to take the lens cap.
That makes you real skeptic, doesn't it? Can't really see anything.
So yeah, yes. So, but yeah, Michael Shermer has a really good podcast that is worth listening to sometimes. Anyway, so yeah, that's pretty much all I got.
Yeah, thank you for taking
Yeah,
the
thank
time
you.
to put all that together.
Okay, so there is no meeting, normal meeting in. Thank you.
December.
Thank you. So there is no general meeting in December because of the holidays and because we're going to have the Christmas party. January that's when Mike Ford is coming. I think that's what we decided.
That's down now. you and Mike Ford need to confer a little more, because I don't know where he's, he has a tendency to kind of forget things,
Okay.
so you need to keep reminding him.
Well, I've emailed him maybe twice and not heard back, so either I'm maybe sending it to a wrong email, or maybe he's just kind of,
Gmail.
sounds right.
MJ 2000 or something like that.
So I don't want to pester him
Yeah.
yet.
Yeah.
I figured I'd start pestering him probably sometime around the first of the
Give
year.
yourself plenty of time.
But if for some reason, and I think what he wants to talk about is basically the Banner Science Center, right, and the possibilities
Well,
of.
and kind of introduce the Banner Creek Science Center to everybody, and also to maybe present a discussion about the possibility of eventually bringing the Tonga up there.
Right.
And given our options of what's gonna happen when the ball diamonds are in full force and things start looking pretty white out there instead of dark,
Yeah.
maybe we can take a look at that as a possibility, at least, of getting the tom ball out in a position where it can be used. And remotely, they've got an internet set up out there too, so.
And it seems like a pretty nice site. I think it's pretty dark. isn't
It's
it?
fairly dark. I would equate it to at least as dark as my site at Sandlot, and not as dark as Far Point could be.
Yeah, but if, like you said, if they build those,
Yeah,
which
well.
apparently they're
that's-
going to
that's-
do.
And it's kind of just an idea of something to consider, if it gets to the point